Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. This is section 11.7 and it's about strategy for testing series. So we studied series in the previous sections from 11.2 to 11.6 and we had a lot of tests for convergence or divergence. And the problem is to decide which test to use on which series. So testing series is similar to integrating functions. There are no hard and fast rules about which test to apply to a given series, but maybe if you follow these steps, it will help you. If it is not wise to apply a list of the tests in a specific order until one finally works. Of course, this is a waste of time and effort. So you don't mm, take each series and start doing one, two, three, the tests one by one. No. The best way is to classify the series according to the form of the series. So try to follow these steps. First, try to find limit an when n goes to infinity. There will be always a series, summation an, and the question is, test this series for divergence and convergence. So find the limit of an when n goes to infinity. If the limit is not zero, if it is infinity, does not exist, or a number which is not equal to zero, then the test for divergence immediately says that this series is divergent. So this may be the first step to, to use. Now look to the series carefully. If it has this form, summation 1 over n to the power p, for example, summation 1 over n, summation 1 over n square, summation 1 over square root of n. Okay, this is a p series. We studied p series before. By the way, please do not continue this lecture until you understand all the previous lectures from 11.2 to 11.6, because this is just a summary for all of them. You should know all the tests before continuing this video. So we studied that a p series is convergent if p is greater than 1, and it is divergent if p is less than or equal to 1. So summation 1 over n is divergent. It's called the harmonic series. Summation 1 over square root of n is divergent because p is half. But summation 1 over n square is convergent. So if it is a p series, you immediately can say whether it's convergent or divergent. If it is not a p series, look carefully again to the form of the series. Is it a geometric series? Is it written as summation ar to the power n minus 1, where n is from 1 to infinity? Or if n starts to 0, so is it written in the form a times r to the power n? So for example, summation 3 times 4 to the power n, okay, or summation 3 to the power n over 2, or summation 1 over 7 to the power n. All of these are written in this form, and they are geometric series. Once the series is geometric, we know that it is convergent if absolute value of r is less than 1. So for example, here r is 1 over 7, and it is less than 1, so this series is convergent. While here, half is a constant, and r is 3, so 3 is greater than 1, so it's divergent geometric series. So if the series is a geometric series, we can tell whether it's convergent or divergent easily. Well, if it is not p series or geometric series, look carefully to the form of the series. Is it similar to a p series or similar to a geometric series? If it is not, summation 1 over n. but 1 over n plus 3, for example. So it's similar to uh, a p series or a geometric series. For example, 1 over 2 to the power n, okay, uh, times something, okay, or plus something. Let me write it like this: 1 over 2 to the power n minus 5, for example, okay. So is it similar to a geometric series or a p series? If it is, then you can use the comparison test, because we use the comparison test when we want to compare the series with a geometric series or a p series. And the comparison test says that if the series is convergent, then less than convergent is convergent. So less than convergent p series would be convergent. Less than convergent geometric series would be convergent. And greater than divergent geometric series or divergent p series would be divergent. So this is the comparison test. And you can check section 11.4 for more information about the comparison test. But pay attention that we use the comparison test when the series has positive terms. If it doesn't have positive terms, if some of the terms are negative or it has negative terms, then you can apply the comparison test to summation absolute value of an, because we studied if summation absolute value of an is convergent, then summation an is absolutely convergent. And for absolutely convergent, please also refer to section 11.5. If you cannot use the comparison test directly, then you can use the limit comparison test, the direct comparison test. If not, you can use the limit comparison test. And the limit comparison test says that if limit of an over bn is greater than 0, then an and bn, summation an, summation bn would be either both divergent or convergent as n approaches infinity. So please also, for more information, study section 11.4. If the series has the form -1 to some power n, or power n minus 1, then we use the alternating series test. And we studied this in section 11.5. Please refer to that section for more examples about alternating series test. Bn in this case has to satisfy two conditions. The limit of Bn when n goes to infinity is 0, and Bn plus 1 should be less than Bn, so it's decreasing. If these two conditions satisfied for Bn, then the series would be convergent. If we have factorials or powers, two powers, okay, or products, something to the power n raised to n, and something raised to the nth power, constant raised to the nth power, 2 to the power n, 3 to the power n, for example, then we use the ratio test. And in section 11.6, you will find a lot of information about the ratio test. If we have nth power, if it is an, and an is written as bn to some power n, okay, nth power, so we can use the root test. More about the root test in section 11.6. And finally, if nothing works of all of these tests, you can apply the integral test. But the integral test is somehow longer than all the other tests. And make sure that the integral, the improper integral, is easily evaluated. When it is easily evaluated, you apply the integral test. Otherwise, you cannot. It's not helpful to apply the integral test. So let us try to solve these examples and determine which test to use. So if you first think of the limit of an when n approaches infinity, you will find that limit of n minus 1 over 2n plus 1 when n approaches infinity, if you take the highest power, the limit is half. And half is not equal to 0. So the series is divergent by test for divergence immediately. Well, here, if you take the limit of an when n goes to infinity, let us take the limit of square root of n cube plus 1 over 3n cube plus 4n square plus 2 when n goes to infinity. Then take the highest power, term with the highest power, square root of n cube, and here 3n cube. Well, I have, as you can see, here 3 over 2, while here 3. So I'll have 1 times 3 to the power 3 minus 3 over 2 is 3 over 2. And then the limit would be 0 as n goes to infinity, because 1 over infinity is 0. So the test for divergence doesn't help here. But as we studied in section 11.4, if you take the highest power, which is, if you take bn 1 over 3 times n to the power 3 over 2, which is this one. If you take this as bn and you use the limit comparison test. So this is an and this is bn, and bn is a multiple because 1 over 3, a multiple convergent p series. Why? Because p is 3 over 2 and it's greater than 1. So if we use the limit comparison test and find the limit of an over bn, we will have an over bn multiplied, we change division to multiplication by the reciprocal, and taking the highest power now, if you multiply n to the power 3 over 2 times n to the power 3 over 2, you will have n to the power 3. And we have the term with the highest power here, 3n cubed, so the limit would be 1, which is greater than 0. So by the limit comparison test, summation an also converges because summation bn is convergent. So this is, we can solve this series by limit comparison test. Here, this series, we solved this series by integral test, if you remember, because the derivative of negative n square is negative 2n, so the derivative is outside. So you can solve this integral. You can solve the integral x e to the negative x square easily by substitution, easily solved. So you can use the integral test. And also, we solved this using the ratio test. So if you take an plus 1 over an, would be, I will write this as n over e to the power n square. This would be an. So an plus 1 would be n plus 1 over e to the power n plus 1 squared multiplied by e to the power n squared over n. And this is what? This is e to the power n square if you expand n plus 1 square plus 2n plus 1. So I can cancel en square with en square, and I will still have n plus 1 over n, okay? Absolute value, everything is positive, times 1 over e to the power 2n plus 1. And when I take the limit when n goes to infinity, so this quantity will go to, the limit of this is 1, but the limit of 1 over e to the power 2n plus 1 is 0 because e to the power infinity is infinity, 1 over infinity is 0, and 0 is less than 1. So by ratio test, this series is absolutely convergent. Series is absolutely convergent. Well, here we have negative 1 to the power n. So we can use alternating series test. Okay. Especially if you notice we have n cube over n to the power 4 plus 1. So if you want to use comparison test, you will compare it with n cube over n to the power 4, which is 1 over n. 1 over n. And 1 over n is the harmonic series, divergent. So actually, this means that summation n cube over n to the power 4 plus 1 is divergent by, you can use the limit comparison test for that, by limit comparison test. So I will use the alternating series test here. Alternating series test says that this is Bn, and we need to check that limit Bn is 0. And that's correct because when we take the highest power up and down, we will have 1 over n. And the limit of 1 over n when n goes to infinity is just 0. We just need to make sure that it is decreasing, Bn is decreasing. And because I have n above and n below, so I will write this function and prove that it is decreasing for n greater than or equal to 1 or maybe 2, whatever. So f prime of x, I'll use the ratio, the quotient rule. Derivative of x cube is 3x squared minus derivative of x to the power 4 plus 1 is 4x to the power 3, and I have x to the power 3 in the numerator. So let me take x squared as a common factor. So I'll have 3x to the power 4 plus 3, because I took x squared as a common factor, minus 4x to the power 4 because I took x squared as a common factor, over x to the power 4 plus 1. So f prime of x is equal to x to the power 4 plus 1 to the power 2, and I have x squared here, and 3 minus x to the power 4. 3x to the power 4 minus 4x to the power 4 is negative x to the power 4. So I can see that this is x squared, always positive, x to the power 4 plus 1 squared, always positive. So f prime would be negative if 3 minus x to the power 4 is positive. Well, the 0 of 3 minus x to the power 4, to find its 0, I put it equals to 0. So x would be the fourth root of 3. And the fourth root of 3, if I use the calculator, is 1.3, approximately 1.3. So I can see that if x is greater than or equal to 2, okay, greater than 1.3, let me say 2, greater than or equal to 2, then f prime of x is negative. If you choose any number greater than 2, 3 for example, 2, 2.1, this would be negative. F prime would be negative. This means that f is decreasing for n greater than or equal to 2. For x, of course, talking about x. So Bn is decreasing for n greater than or equal to 2. This means that summation negative 1 to the power n, which is n cube. Let me just write an, sorry. Summation an from 2 to infinity is convergent by alternating series test. And this means that summation an from 1 to infinity is also convergent because we are adding only one term. So this series is convergent using alternating series test. Here we have factorial 2 to some power. So immediately I use ratio test. AK plus 1 over AK. 2 to the power k plus 1 over k plus 1 factorial divided by or multiplied by k factorial over 2 to the power k. This cancels with this. And I'll have 2 here. This cancels with this, and I'll have k plus 1 here. So I have 2 over k plus 1. When k goes to infinity, this goes to 0. 2 over infinity is 0. 0 is less than 1. So summation an is absolutely convergent by the ratio test. Well, here I have 2 to power 1, okay, and there is a plus 3 to the power n. So the limit of this is 0 when n goes to infinity. Test for divergence is not there. But this is similar to 1 over 3 to the power n. So if this is an, and if I take bn as 1 over 3 to the power n, I know that summation 1 over 3 to the power n is a convergent geometric series, since absolute value of r is equal to 1 over 3, which is less than 1. So this is a convergent geometric series. And 1 over 2 plus 3 to the power n is less than 1 to the over 3 to the power n, because 2 to the power 3n is greater than 3n. So when we take the reciprocal, it becomes less than. And this is the comparison test. So immediately by comparison test, summation an is also convergent, because less than convergent is convergent by direct, can say direct comparison test. Two similar looking series are given. Test each one for convergence or divergence. Well, this is a convergent geometric series, since R is 1 over 5 and it is less than 1 immediately. And here 1 over 5 to the power n plus n is less than 1 over 5 to the power n, since 5 to the power n plus n is greater than 5 to the power n. So the reciprocals would be less than if we take the reciprocal. So by direct comparison test, summation an is convergent because summation 1 over 5 to n is a convergent geometric series. R is 1 over 5 less than 1. Okay, we already uh, found, we already talked about this series. It is part A. Well, I have here negative 1 to the power n, so this is, I can use the alternating series test. But I notice that absolute value of negative 1 to the power n over n to the power 3 over 2 is 1 over n to the power 3 over 2. And summation 1 over n to the power 3 over 2 is a convergent P series. Why? Since P is 3 over 2 greater than 1. So summation an, this is an, is absolutely convergent. Because when I take the absolute value, I found that it's convergent. So summation an is absolutely convergent. Please check section 11.5. There are many examples like this one there. And this one is a convergent P series. Since P is 3 over 2 greater than 1. And of course, this is also absolutely convergent if you like, because all the terms are positive. So if you take the absolute value, it would be the same. So this is also absolutely convergent. You can mention that it is convergent or absolutely convergent, unless he asks for whether it's absolutely convergent or not. It is absolutely convergent. Well, here I have 3 to the power n, I have n, so I will use the ratio test. an plus 1 over an. So n plus 1 over 3 over 3 to the power n plus 1 times 3 to the power n over n. There is a cancellation. This with this, I'll have 3. And if I take now the limit, this would be n 1 over 3 times n plus 1 over n. If I take the limit when n goes to infinity, this goes to 1 over 3, which is less than 1. So series is absolutely convergent by ratio test. Also here I have power and n, so I'll use immediately the ratio test. And if you notice, this is the reciprocal of this. So I'll have 3 to the power n plus 1 over n plus 1 times n over 3 to the power n. And I will have 3, in this case, 3 times n over n plus 1. And the limit of this when n goes to infinity is 1. So the limit would be 3, and 3 is greater than 1. So series is divergent by the ratio test. Of course, these cancels and you will have 3 up. Well, here, if you find the limit of an, you notice that it is 1 and 1 is not 0. So series is divergent by test for divergence, the first test we mentioned. While here I have negative 1 to the power n, the same series, but I have negative 1 to the power n. Okay, I found that the limit of this is 1. So the limit of negative 1 to the power n plus 1 over n when n approaches infinity does not exist because it's plus or minus 1. Okay, does not exist because the limit of this is 1. So the limit of this would be plus or minus 1 or does not exist. It doesn't reach a specific number. So series is divergent by test for divergence. And I did not use the alternating series test here. If you look here, if you take the highest power up and the highest power down, you will have 1 over n. So you can compare this series to 1 over n. But n plus n square plus 1 is less than n over n square, which is 1 over n. So this is less than 1 over n. To use the direct comparison test, it has to be greater than, because greater than divergent is divergent, because we know that this is the harmonic series and it is divergence. So I cannot use the direct comparison test, but I can use the limit comparison test. So let me find the limit of an over bn when n goes to infinity. So an is this one multiplied by n. So I'll have n square up and n square down. So if I take the term with the highest power, the limit is 1. And that's greater than 0. So by limit comparison test, series an is also divergent, since summation 1 over n is the divergent harmonic series, or you can say that it is a p series with p equals to 1, so it is divergent. Here it is the same series, but he raised it to the power n. Since I have power n here, let me use the root test. So the nth root of a to the power n with absolute value, this will give me n over n square plus 1. And when n goes to infinity, this will go to 0. 1 over n, 1 over infinity is 0. And 0 is less than 1. So by root test series, this series is absolutely convergent. All right. Now, what about this series? We mentioned this series in the integral test. You can solve this series by integral test, and it's easy to find the integral of ln x over x dx. You take ln x as u, and it is positive, decreasing. You need to prove it's decreasing, okay? But I can also use comparison test. I can compare it with 1 over n. I know that summation 1 over n is divergent. It is the harmonic series. Okay. But can I prove that ln n over n is greater than 1 over n? Actually, this is correct because ln n is greater than 1 for n greater than or equal to 3. Starting from 3, ln 3, ln 4, ln 5, all are greater than 1. So because of that, summation from 3 to infinity of ln n over n is divergent, sorry, by direct comparison test. Hence, summation from 1 to infinity of ln over n is also divergent. because if you add two or three terms to a divergent series, it will remain divergent. So put this in your mind. You may use this in the comparison test. Okay, len n greater than 1. While here, uh, I have to use the integral test. I cannot compare it with 1 over n. I would like to compare it with 1 over n. But I don't have a direct way to prove that this is greater than 1 over n, because len n is greater than 0. So n len n is greater than n. So actually this is less than this, not greater than. So I can use the integral test. And if you remember, for the integral test, we have 1 over x len x. This is the y, the function. This is positive, of course, and continuous for n greater than or equal to 10. N starts from 10 here. And to prove that it is decreasing, we solve it actually. This exercise, we solved it exactly in the integral test. So y prime, if you find y prime here using the whatever you like, quotient rule or the rule with derivative of 1 over u negative u prime over u square, okay? You can use this formula to find that the derivative is negative 1 plus len x over x square len x all square. You can see that here everything is positive in the denominator. So for y prime is less than 0 because negative times this. For x greater than or equal to 10. If you put 10, len 10 is positive. So this is positive times negative. So y prime would be negative. This means that y or f is decreasing for x greater than or equal to 10. So now we can find the integral from 10, the improper integral, and check this improper integral. The integral test says if the improper integral is divergent, the series would be divergent. If it is convergent, the series would be convergent. If you remember, the definition of the improper integral is like this. We call infinity t, and we take t to infinity. And for more exercises, please go to the section about improper integral in chapter 7, I think 7.8. X len x, okay? And now how to find the integral of 1 over x len x? Well, let us find it here. I call u len x. Du would be 1 over x dx. So I'll have 1 over x dx is du, and I have 1 over u du. So the answer would be len u, and this would be len u. Okay, for x greater than 10, not len u, len x, because u is len x. And the absolute value is not needed because n here starts from 10. So this would be equal to the limit when t approaches infinity of len x from 10 to t. And this would be equal to the limit when t approaches infinity of len t minus len 10. But len infinity is infinity, len infinity is infinity, infinity minus this number is infinity. So the answer is infinity. So improper integral diverges. So this means that summation an diverges by integral test. So this is an example about the integral test. Well, if you look here to this series, I have 1 over n plus n factorial. The series, if I take bn 1 over n factorial, this series is absolutely convergent by the ratio test. And you can check that an plus 1 over an would be 1 over n plus 1 factorial multiplied by n factorial. So it would be 1 over n plus 1, and it goes to 0, and 0 is less than 1. And it's clear that 1 over n plus n factorial is less than 1 over n for all n, 1 over n factorial. So by direct comparison test, summation an is convergent because summation 1 over ni in factorial is convergent. If you want to compare it with 1 over n, well, this is not greater than 1 over n. This is less than 1 over n. So that's why I tried 1 over n factorial. While here, this series is divergent immediately. Why? Since it is the sum of the harmonic series, and the harmonic series is divergent and a convergent and summation 1 over n factorial. Of course, this is convergent. We have just proved it. So sum of divergent plus convergent will be divergent. So this series is divergent. Here, I can compare this with 1 over square root of n square, the highest power. And this is 1 over n. But 1 over square root of n square plus 1 is in fact less than 1 over n. It is not greater than. And I know that 1 over n is divergent. So I should use the limit comparison test. I know that summation 1 over n is divergent. It is the harmonic series. And now when I take the limit of an over 1 over n or times n, I will have the limit when n goes to infinity. This is the term with the highest power. And this is the term with the highest power. This is n over n is 1. 1 is greater than 0. So by limit comparison test, summation an is divergent because summation 1 over n is also divergent. While here, if I take bn 1 over n square, so 1 over n times n square plus 1, this is a plus, so I can write it less than this. And square root of n square is n, so this is in fact 1 over n square. And summation 1 over n square is a convergent p series since p is 2 greater than 1. So by direct comparison test, summation an is also convergent. This is enough. I'll stop here and I'll continue more examples about series in the next video.